In this video, we'll be giving a high-level overview to the concept of emergence and the different aspects to it that we'll be covering in more detail in future modules during the course. The dictionary definition of the term emergence comes from the Latin word meaning bringing to light. In this sense, it means the process of becoming visible or coming into existence. In its most abstract and metaphorical sense, emergence describes the universal process of creation that is both a very fundamental and pervasive feature to our world as it plays out in all types of systems. Emergence involves the creation of something new that could not have been expected from a description of the parts prior to its creation. Indeed, the 17th century Latin meaning to the word meant something similar to unforeseen occurrence. This novelty to emergence comes in a spectrum of strengths. These strengths account for the different types of emergence, which are described as being strong or weak. At the weak end of the spectrum, the novel phenomena may only appear different, while after its arrival, it is possible to understand how it derives from some set of elementary parts. At the strong end of the spectrum, one thing is caused by another, but it is in no way reducible to the elementary parts. Classical examples of emergence can be found in the collective behavior of social insects like ants and bees as they create swarms and colonies. Many other examples have been identified in human social organizations and human cognition. The solvent properties of water is an often cited example of emergence, for neither hydrogen atoms nor oxygen atoms in isolation possess this property, and neither do they possess scaled-down versions of the property. Thus, solvent action seems to emerge from a nonlinear combination of the properties of hydrogen and oxygen. Because emergent properties are a product of the synergies between the parts, they cannot be observed locally in the subsystems, but only as a global structure or integrated network. In such a way, emergence creates a system with two or more distinctly irreducible patterns of organization called integrative levels. Thus, new descriptive categories are necessary for the different levels when referring to phenomena that involve emergence, as emergent macro-level phenomena cannot be described within the vocabulary applicable to the parts. These emergent features require new terms and new concepts to categorize them. As an emergent phenomenon is thought to be irreducible in some sense to an account of its elementary parts, a true emergent phenomenon is one for which the optimal means of prediction is computer simulation. A primary distinction within the philosophical study of emergence is often made between what is called ontological and epistemological emergence. Epistemology refers to knowledge and how one knows the world. Epistemological emergence is the idea that some systems cannot be described as a matter of practice in terms of their component units because of the limits to our knowledge. That is, our inability to obtain all relevant information and do all the computations. Ontology refers to the nature of being. It is concerned with what we consider the objective being of things in the world around us. With ontological emergence, we're not just making statements about our own knowledge of the world, we're making statements about how the world actually is. When we talk about ontological emergence, we're making a statement about how the world is, irrespective of our understanding of it. If ontological emergence is identified, it means a full understanding of the system in terms of its components is not possible in theory, not just because of practical constraints, but because new and fundamentally irreducible levels of organization appear at higher levels. Whereas the term emergence is of major interest in philosophy and art, it is understood in systems theory in more scientific terms, with reference to nonlinearity, synergies, self-organization, and pattern formation. In this context, emergence describes a process whereby component parts interact to form synergies. These synergies then add value to the combined organization, which gives rise to the emergence of a new macro level of organization that is a product of the synergies between the parts, not simply the properties of the parts themselves. Emergent properties are attributed to whole structured collections of elements, where the emergent property is not an additive function of the properties of the elements of the collection taken individually. For example, the mass of the human body is a simple summation of all of its parts taken in isolation, and thus it is not an emergent feature. However, human consciousness would appear to be an emergent phenomenon, as we're not able to provide an account of it as some summation of elementary cognitive parts. The behavior of the system results more from the interaction of the components than from the behavior of the components themselves. The added value of the whole that exists above and beyond that of the parts and their properties is a product of the way they interact. These specific interactions between the parts that add or subtract value from the whole organization are called synergies. Emergence is then a product of synergistic interactions between the parts in the system. Positive synergies arise when two or more elements both differentiate their states and activities with respect to each other and coordinate them. Differentiation enables the parts to specialize, while integration enables them to coordinate their different capabilities towards an overall outcome. In so doing, the synergistic interaction adds value to the overall system, and we get some combined organization that is greater than the sum of its parts, what we call emergence. These synergies are a pervasive phenomenon in our worlds, in the interaction of pollinating insects and plants, microbial organisms and their host animals, in the interaction between different drugs, and in all kinds of social organization, such as businesses, families, and friendships. Because the parts within a synergy are differentiated and coordinated with respect to each other, this means they have a specific type of interaction, and if we alter that interaction by moving the parts around or recombining them in a different fashion, then the added value may be lost. For example, if we had a lock and a set of keys, with only one of these many keys being able to open the lock, although in their mass and other physical properties, the keys would be almost exactly the same. If we took any key except the correct one and combined it with the lock, this combination would have virtually zero value, as the lock would not open, and thus the combination would be non-functional. But when we combine the right key with the right lock, we will get an overall functioning system that is of value. This added value was derived from the synergy between the key and lock. This specific key and lock were designed to be differentiated with respect to each other and coordinated, thus enabling their combined functionality and the added value. Neither lock nor key could achieve the combined function of securing something in isolation. Thus we need both different parts, but also they need to be working together in some fashion to get the overall functioning system and the resulting emergent organization. The other keys were differentiated from this lock, but they were not coordinated with it, and thus no added value or functionality emerged when we combined them. Synergistic interactions give rise to new levels of organization that have their own internal properties, features, and dynamics. These new emergent levels are called integrative levels. Although these new levels are not directly dependent upon the properties of their parts, the pattern of organization that has emerged is dependent upon the integrity of the synergies between their constituent parts. If we take the synergies away, the integrative levels will disintegrate and disappear. Thus, unlike simpler, linear systems that can be reduced to a single level of organization, emergence results in the development of more than one level of organization, with these different levels representing a different context and set of rules governing the parts. With integrative levels, we get a dynamic where the higher level is dependent upon the lower levels for its existence. However, the higher level also creates its own pattern of organization that feeds back to condition the micro-level elementary parts and their interactions. All emergent systems are composed of a micro-level set of building blocks that place an upward set of physical constraints on the system, but also the macro-level defines a pattern of organization that then exerts a downward effect on the parts by creating the context for their operation. For example, the electrons moving through a microprocessor are the physical building blocks that make possible computation. The processor is one of the physical constraints placed on the macro-level software program that's running on it. However, the program on the macro level is performing some process that is not associated with the organization of the parts, such as a person using it to build a website. Although the macro-level operations of the software is fully dependent upon the micro-level of the physical electrons moving around in the processor, the structure of that macro-level process that the person is performing when they build the website has nothing to do with the underlying micro-level physical processing going on in the computer. This software activity could be conducted in the same way on many different types of computers with very different underlying patterns in the hardware. The upper level of the software is, though, creating the downward effect, conditioning how the electrons move around on the micro level. Due to this development of different levels of organization within the same single overall system, emergence gives rise to a complex dynamic between the different levels, most notably between the macro and micro levels of the system. Systems that engender emergence of some kind have a specific micro-macro feedback dynamic that becomes important to understanding their overall behavior. This dynamic, where the higher levels affect the lower levels, is a key part of emergence, and it is called downward causation. Downward causation is the claim that in a system exhibiting emergence, the higher or macro level, as the locus of emergent phenomena, exerts some kind of causal influence downward on the lower level substrates from which it originally emerged. This interaction can be seen in biological organisms, as the individual organs and tissues create the whole organism, but then the organism as a whole feeds back to regulate the parts. Within societies, individuals create institutions, but then these institutions feed back to constrain the individuals towards the ends of the institution as a whole. Likewise, economies and financial markets involve a constant interplay between the macro structure, such as market prices, and the individual actors on the micro level. In all cases, emergence involves new descriptions of a system being used when we go from the micro levels to the macro level. And this can be seen in many areas of science. For example, economics is divided into micro and macroeconomics, with different terms used in the different domains. Likewise, theoretical physics remains divided between descriptions of physical systems on the micro level in terms of quantum mechanics and on the macro level in terms of general relativity. In the study of society, the micro and macro are divided into two different domains with their own separate lexicon. Psychology for talking about the individual, and sociology for talking about macro-level patterns within social systems. This is because phenomena like social movements only emerge out of the synchronized activities of many individuals, and thus will not form part of the study of the individual, but will only form part of the study of the whole social group. The question that remains, though, is whether we form different descriptions on different levels out of expediency and lack of knowledge. Or do we do it because on a fundamental level it's not possible to fully derive an account of the macro level from the micro level? This difference is captured in the terms strong and weak emergence. Weak emergence describes an emergent process that, given enough information, can theoretically be simulated by a computer. With the process of weak emergence, novel features and properties may emerge within a system that could not have been predicted a priori. However, once they have emerged, it is possible, at least theoretically, to derive them from the underlying component parts, even if in practice this is often not computationally viable. However, strongly emergent processes are ones that cannot be derived, even in theory, from a full understanding of the properties and interactions of the component parts on the lower level. The higher level emergent properties and features must then be understood as a whole in terms of the macro level dynamics with only limited reference to micro level mechanics. As in epistemology, emergence reflects a certain way of looking at the world that may be contrasted to reductionism. The idea of emergence can be identified as one of the very few central ideas behind systems theory and the holistic paradigm. Both holism and reductionism lead to very different ways of seeing the world and fundamentally different approaches to conducting science. The central question dividing the two paradigms is whether our world is expressed by just a few basic laws, which directly govern the most fundamental parts of nature, and through them the more complex systems they compose. This would be the position held by analytical reductionist approaches, and leads naturally to a focus on studying ever more basic elementary parts. Or in contrary, whether emergence is a fundamental and irreducible part of our universe, in which case it would not even theoretically be possible to reduce everything to an account involving only basic elementary parts, and thus we should focus our inquiry in understanding the abstract principles governing the patterns of organization that emerge on different levels. This would be the position held by the more holistic approaches in the system sciences. The basic reductionist intuition is that worldly events and processes are governed by just a few basic properties, which are linked through just a few basic physical laws, which results in what is called the completeness of physics. Everything that is physical, and every event, phenomena, or process is caused by some low-level physical change in the component parts. The classical reductionist conception of the structure to the enterprise of science was provided by Oppenheim and Putnam in 1958, who made explicit a widespread view of the sciences as a hierarchical structure, with the domains of sciences higher up being shown to be composites constructed out of the entities of science lower down. This hierarchy can be thought of as a pyramid, with reductionism as the means for moving up and down its levels. At the bottom level, we have fundamental physics. Above this, we have other areas of physics. Then upwards, chemistry, biology, psychology, economics, and other areas of the social sciences. The result of this is a somewhat alienating view of the world, with fundamental physical particles at the center, and human activity as some form of peripheral activity, leading to a knowledge base that is very much removed from our everyday experience of the world. This idea of emergence leads to a very different conception of the enterprise of science, one that does not try to break things down, but instead looks at the many different levels to find patterns and processes that are common across all. This approach is grounded in abstraction, through identifying patterns that are common to all types of systems on all levels. Holistic approaches try to understand the basic process of synthesis, synergies, and the dynamics of change that are seen throughout all kinds of systems. Instead of reducing things to a limited subset of physical elements and laws, it actively seeks diversity to derive the abstract patterns that emerge on all levels and are common to all systems. Here, the unity of science that both reductionism and holism seek is not looked for in elementary parts, but instead is looked for in abstraction, abstract models that apply to all systems, social, physical, biological, engineered, etc.